Thank you, Dr. Martin. Good morning, everyone. My name is Danielle Baroni. I'm the team lead for Project CAM, and with me are Aidan Moore, Ryan Bertucci, Sean Rager, Alex Lubiarz, Sean Prendergast, and Philip Belterman. And today we're going to be presenting to you for our system verification review. So Project CAM was created to create a solution for the Micro-G Next Challenge that is sponsored by the Neutral Buoyancy Lab at Johnson Space Center. And the challenge that we're participating in is called the EVA Camera Attachment Mechanism Challenge, where the purpose is to attach to 3 different interfaces found on the ISS and only use manual power and be EVA operable for the astronaut. And the reason for this is that currently astronauts only have a first-person view when sending video back to mission control, and we want to provide a third-person view, and that way the mission controls can have a better view of what they're doing. And an example of 2 of the interfaces for scale, the top one is the EVA handrail, and the one below it is the CD card frame. And as of last semester, we found out we are participating in the challenge, so the purpose of this semester was to fabricate and test to make sure we're ready for the Neutral Buoyancy Lab. So since our PDR last semester, we've gone through some changes. Our original design was composed of 3 subsystems: the camera mount subsystem, the arm subsystem, and the base subsystem. And we figured through this semester that we can combine 2 of them, being the camera mount and the arm subsystem, and reduce down to 2 subsystems, and several other changes that happened in that course. So in the beginning, the base subsystem started off very simple, just to clamp around each of the interfaces, and our base subsystem lead moved on to a claw mechanism, and after testing and verifying that it can attach to all 3, we landed on a more current design. And for our arm subsystem, we went through a complete redesign through our fabrication process after we found out that our double ball joint design would not be able to have enough frictional force to hold the weight of the 2 arm linkages. And that led us to our more current design, where we have Revolute joints that have locking teeth that will keep the arm linkages in place. And we also changed the cross-section of the arm linkages to have that of the EVA handrail that I mentioned earlier. And that way the astronauts have a more recognizable surface to maneuver around and be able to attach it to other current tools that they use. So now I'm going to hand it off to Aidan to talk about our base subsystem requirements.
Thank you, Danielle. So we went through several tests to verify that the base subsystem met our fabrication and functionality requirements. The first test was to verify that the 2-fault tolerance system, which is this system right here. What it is it is an automatic locking piece that is engaged when the squeeze to release handle is depressed. So after the EVA astronaut attaches to any of the interfaces, this metal piece will self-engage. That way it can't be knocked off or fall off imminently. So this was verified through testing and met its requirement. The next requirement we tested for the base was to verify that it could attach to all of or at least 2 of the 3 interfaces. The first being the EVA handrail. As you can see here, the base was designed specifically to attach to that, as well as the seater cart shown here, and the truss frame here. So we met all 3 of the interfaces, the interface requirements. The next requirement that we tested was to ensure that the tether attachment was accessible and usable. The tether attachment itself is located right here. We decided to put it on the base subsystem as it was the most stable portion of the entire system. In the image on the right, you can see that we actually attached a carabiner during our Equis compatibility test. This was to show that it is accessible during use and for whatever the astronaut might need it for. And now, so we also did some volume and some weight measurement tests. We came in underweight and within our volume constraints. The total weight was about 3.5 pounds for the base subsystem itself, so well under that 7.5 pounds. But we also met all of our requirements. And I'm going to pass it off to Ryan to talk about functionality.
Thank you, Aiden. All right, so first I'm going to go over the internal operations of the base subsystem itself and how it actually works. As you can see here is a cutaway of the base. Shown in red is the internal compression spring. That provides a positive force throughout the entire operation of the base subsystem. What it does is provides a pressure on the top plate of the internal surface of the base, as well as connecting to the tension nut. This provides a positive force pushing the claws into a closed position at all times. The tensioning nut also allows us to vary the tension within the system itself so that we can increase the tension or reduce it per the needs of the astronaut. If it's too high of a tension, then they won't be able to pull the handle. If it's too low, then it might fall off of the intended interface. We also incorporated a torsion spring in the locking mechanism. This allows it to be a self-engaging locking mechanism where it will automatically engage once the base is attached to its intended interface. Going into a computer simulation of how the base operates, it's a very simple operation in that you disengage the two-fault locking system, you squeeze the handle to open the claws, you determine the interface that you would like to connect to, place the base on the interface in its respective position. Once you have the base positioned where you want it, you release the handle, and as I said, the secondary locking mechanism automatically engages and holds it in position. With that, I'll give you a quick demonstration using our test stand to show proof that it does in fact work. As I said, it's the same operation for all three interfaces. You simply disengage the secondary locking mechanism, release the handle, and it engages. It's supposed to engage. Technical difficulties. There we go. Fairly simple operation, rather intuitive, and it locks in place on all three. And as I said, the secondary locking mechanism does prevent it from releasing unless you disengage the secondary locking mechanism. With that, I'm going to pass it off to Sean to go over the ARM subsystem.
Thank you, Ryan.
Do I have, oh, I missed a slide. I apologize, let me cover that real quick. Last minute slide entry. Our NASA mentor also recommended that we introduce a Bayonet Probe. Bayonet Probe is on many of the tools that astronauts currently use. And what it does is it allows the astronaut to attach the tools to an EVA utility belt. The probe simply inserts into a receptacle on the belt and locks it in place. The design shown here is NASA's design. We changed the design slightly and allowed it to be a revolving connection point so that when it is attached to the utility belt, the camera or the subsystem can actually be manipulated out of the astronaut's way so that it's not encumbering them during EVA operations. Now, I will pass it off to Sean.
Thank you again, Ryan. So for the ARM subsystem, underwent several stress tests to ensure that both the linkages and the arm joints would meet the 20-pound force requirements set by the team. As you can see on the screen, this is our setup for our test. The arm linkage was secured into a table-mounted vise with a test linkage actually secured to, or the test joint secured to the linkage. This was to ensure that we wouldn't accidentally strip out the threading from any of our manufactured joint pieces, given that the arm linkages and all of our components are made of aluminum to help satisfy our 4-pound subsystem weight requirement. This joint was attached to the linkage through a threaded connection rod, And at the end of testing, the linkage and the threaded rods were examined to determine if there was any damage done during testing. No damage was seen on either the linkages or the arm joints. So to ensure that CAM was able to meet the range of motion requirements set by the competition, the team designed joints that were able to move in a complete circle. As is shown on the screen, each of the arm linkages was attached to one half of the Revolute joint, with each of the movements of the teeth on this joint representing a 30-degree rotation. This 30 degrees was tested on a comparator in our on-campus machine shop, and this was just to ensure that the 30 degrees that had been machined were to the intended specifications. Now, making sure that the arm linkages and the joints were able to be used with an EVA glove on was a major design requirement for this competition. If they can't use it with an EVA glove, they can't use it on an EVA mission. So this prompted some sizing requirements for the joints and for the size of the arm subsystem. Each of the joint handles was supposed to be manufactured at no less than 5 inches in diameter, and the entire length of CAM was supposed to be no greater than 33 inches in length. Now, each of the arm joint handles was manufactured at 5 1/8 inches apiece, and the entire extended length of the arm from the joint center to the center of the ball joint of the camera mount was 23 inches when fully extended. Now, all of this helps with the storage of CAM, the foldability of the arms, as well as the small size of the arms to help fit us within our volume specifications that were a requirement for the competition through NASA. I'm now going to hand it off to Alex Lubiars to talk about the ARM subsystem a little bit more in depth and to also give you a demonstration of the system.
Well, thank you very much. All right, so the ARM subsystem met all its requirements. The ARM subsystem is comprised of 3 main components. These 3 components are the joints, the structural linkages, and the camera mount. So the first thing I'm going to go over is the joints. So each joint is a locking tooth joint. It is a Revolute joint, meaning it has 1 degree of freedom rotationally. The way it works is it has 2 separate cylinders with locking teeth. When the handle is at rest or left alone, springs between the handles force the 2 cylinders together, locking the teeth together and preventing the joint from rotating. But when a user squeezes the handle together, depressing the springs, the 2 cylinders will separate, allowing the 2 cylinders to rotate independently. Now, this cylinder that's closest to the joints will rotate freely, while this cylinder is rigidly connected to the handles, meaning that when rotating the handle after depressing the joint, that handle will control the movement of the arm, which I will now demonstrate. And like I said, releasing the joint allows it to lock in place. It can be locked in one of 12 positions. Another interesting feature of the joint is that it is clocked, as shown here, with special markings that denote each position from a 1 to 12 scale, just like a clock. So for example, this would be 12 o'clock position, and 6, and everything else. So they're all denoted, and this is joint B, which is the further joint, and joint A is the joint near the base. And this allows mission control to tell the astronaut, for example, put joint A in position 3, point joint B in position 6. And then that would correspond to some movement and place CAM in the correct configuration without the astronaut having to think too hard. The second structure is the structural arm linkage. The structural arm linkage was modeled exactly after the EVA handrail that's placed on the outside of the International Space Station, shown here. This allows the astronaut to have a familiar surface when gripping CAM. It also allows any other system that interfaces with an EVA handrail to interface with our system using the structural arm linkage. The third component is the camera mount. Now the camera mount is a 4-component piece. It's comprised of a spherical ball joint that has a GoPro attachment mount to it. GoPro has a proprietary 3 to 2 prong mounting system, as shown here. So we purchased that joint to make sure that it would interface with that, and then we fabricated our own socket to hold the joint. The socket is comprised of 3 big pieces. The first is the base piece, which has a hemispherical pocket milled into the center of it to hold the ball joint. And then the top retaining plate separates into 2 pieces so that we can get it around the stem, and then comes together and is screwed down by 4 bolts to retain the ball joint and make sure it does not leave the socket. The end result is a joint that works kind of like the rear view mirror in your car, where you can stick it in a position and it'll stay. And this joint allows for 45 degrees of pitch and roll, while the yaw is taken care of by both the joint and the GoPro mount itself. Next, I'm going to pass it off to Sean Prendergast for integration.
Thank you, Alex. Okay, so in this section, we've already covered the arm and the base subsystems. Now we're going to talk about the requirements that the entire system had to meet to succeed at the MBL. One of the things we were most worried about was, is this system going to be safe for use by someone wearing an EVA spacesuit? So to test this, we put on an EVA glove, and we put a latex glove over the EVA glove, and the tester just practiced using CAM and then ran their hand over the surface of the arm subsystem and just was looking for any pinch points or any sort of sharp edges that might rip that latex glove. As you can see, after examining the arm subsystem, we didn't find any sort of pinch points or sharp edges, so that was considered a pass. And then in the base subsystem, we did find two sharp edges that came from extruding pins that actually did rip the glove. So we considered that test a failure, and we deemed the system not safe to use for an EVA space glove because of those pins. To fix that, we actually refabricated the two pins and we replaced them so that they, instead of extruding, are now flush with the surface of the base. And now the glove will no longer come in contact with the extruding pins, and that test is now considered a pass after we re-examined it and redid the test and did not find any sort of pinch points or sharp edges. Thank you. Now I'm going to pass it off to Phil to talk about our last test.
Thank you, Sean. So our last major test was our Equis compatibility test. This was to validate our ease of use and our manual power. And before I show you the video from our testing underwater, I just want to point out a few things. We had our own team member, Aiden, who was our master diver for this. He wore a welder's glove as a simulated EVA glove. And a few things that you may notice throughout this is the arms can rotate freely. This was because we had not finished fabrication at the point. The joints and arm linkages had not been glued, but since have been, and the two-fold system was not fully operational at the time, but now it is. So without further ado, here's our Equis compatibility test. So we started with a vertical test towards the top of the pool because the way gravity works, when CAM would be mounted to an interface, the weight of it could cause the gripping mechanism to part a moment and maybe fall off the interface. But as Aiden just did, he was successfully able to attach to the truss. Kind of gives a little wave to the camera right here. Then he moves on to the CETA cart. Now, as we were kind of talking, NASA's looking for another point of view for testing. We had Sean Prendergast float off to the side with a GoPro chest mount. This is kind of what we're trying to make with CAM. It would be off to the side. You have a greater visibility of the EVA work area. And now Aiden is rotating the arm joints underwater with the welder's glove to see how easy it is to squeeze the locking mechanism. Then we did another series of tests where we had the test stand be horizontal. This is now at the bottom of the pool, and the chest and the GoPro was now on Aiden's chest. This also helps to simulate what it's like for an astronaut during an EVA. Although they use helmet-mounted cameras, Aiden has his on the chest, but the first-person view show that there's not as much visibility as having a third-person view. So you just once again started by attaching to the truss, the seat cart grid, and then finally the EVA handrail. And then after attaching to the handrail, he once again moved the arms around to verify their ease of use. So one thing that we thought of afterwards with this testing was we could have had a third-party diver for the test, as when we go to the Neutral Buoyancy Lab in June, we will have to teach the NASA divers how to use our device, and because with Aiden, he knows how the system works, so it would just give us some practice going forward. And then CAM passed all of its critical requirements that were set through various tests, as shown. It was the user safety, manual power, and EVA operability, but it was also able to pass the weight, volume, approved materials, and drain hole tests. I'm now going to pass it back to Daniela to talk about our conclusion.
Thank you, Phil. So in conclusion, we met all our system level requirements through testing. We met through all our subsystem level requirements through testing. Not all of them were mentioned, but we have conducted those tests. And then 2 significant lessons that we learned throughout this process was learning how to implement a redesign while also keeping a fabrication schedule after we realized that the double ball joints would not provide enough frictional force to withstand the weight that it would have to support. We decided to move on to the Revolute joints. But to be able to do this, we needed to get the permission from our professors, we needed to get the permission from the machinists and ASFAB that it's possible, and we also needed to get the permission from the NASA officials that we can bring this design to the Neutral Buoyancy Lab. And our second lesson learned was with fabrication itself. ASFAB does have the equipment that we need, but by having so many capstone projects, you have to learn how to share and be able to keep your schedule going while also not having as much access to these equipments as possible. I'd like to take the time to thank our faculty at Embry-Riddle, our professors, Dr. Martin and Professor Mangum, as well as Dr. Sensmeyer for approving our project, and the machinists over in AXFAB, Patrick, Jeff, and Jared, as well as Philip Hess for allowing us to test in the pool. We'd also like to thank the URI grant for helping us with our travel arrangements, Dr. Bencher and Virginia Magon, and our Neutral Buoyancy Lab mentor, Scott Ray, who's also a Prescott alumni, which is really cool. And we'd like to thank our panelists for coming here today and watching our presentation. And in conclusion, Project CAMP has met all our requirements needed to be able to test in the Neutral Buoyancy Lab, and now it's just the final touches before traveling to Houston in June to be able to test. Any questions?
Nice job. My name is Jody Davis, and I'm at NASA Goddard. And I thought you guys did a really good job. It's a really neat design and a neat project. To be able to have something up on ISS could be amazing. So a couple things. There was, and I know you guys didn't have enough time to go through the details of your requirement verification for every requirement, because I'm sure you had a lot. There was one requirement that said no damage to ISS. So how did you consider that verified?
Sure. The way we tested that was we created the device out of a soft aluminum, and our test stand is created out of a similar material that is found on the ISS. While attaching to each of the interfaces, we inspected each interface to see if there was any damage incurred by attaching to the interfaces, and finding none, we determined that it was successful in not damaging the ISS.
Okay. A lot of these requirements kind of seem, they're pretty qualitative to me. Were there a lot of the requirements flowed down to you from the NASA project?
Yes, we were given a basic list of all the requirements from the NBL, and we focused on all of those for our project. We had an additional strength test to be able to withstand the 20 pounds, as Sean Rager mentioned, and that was the only additional test that we felt necessary because it was all covered through the challenge.
Okay. And then, any time we change from NASA Heritage flight hardware, there's usually a lot of justification involved because when you have something that's qualified, that's like gold to have something that's already flown. So the Bayonet design, you guys modified it. How did you verify, qualify that modification since it was changed from the original design?
That wasn't necessarily qualified. It was an additional design implementation at the very latest stage of construction. In fact, it was only completed last week. It was, as I said, it was implemented so that we don't know exactly what the best location is or angle to position the bayonet. So we decided that a revolving joint would be the best solution so that the astronaut could determine where exactly they would want it located. We can further the design by creating a locking portion to it so that they can put it into a position, lock it in place, and then it's stable. But again, that was just determined because we don't know at what angle would best suit the astronaut's needs.
Those were requirements that
Correct.
that JSC gave you guys. And then the other thing, again with the qualitative assessment, the pinch point test that you guys did, to me it was pretty qualitative, and it could be variable in how you're testing that. The pressure at which you're kind of smoothing your hand over the hardware. Did you have any machining specifications when fabricating your piece parts so that you had no jagged edges, things were smoothed over? Because that's very important.
I'll give this to Alex.
So during the fabrication process, we did ensure that all edges were deburred. That was made a point to do that. And then essentially the requirement stated that to minimize sharp edges. So we took that to the best of our ability. We minimized as much as we could by deburring everything we could. And then we came up with a test that we thought would be fitting for at least ensuring that there's no sharp edges that would be blatantly dangerous. And we're going to be constantly working to minimize sharp edges as seen fit. So we're going to be constantly checking any new part we put on it to make sure that there's no sharp edges.
Okay, I didn't realize it was minimize sharp edges, so that's a little different. And then the last thing, in the pool test, you only had one welder's glove on, and then the other hand was free. So I think, wouldn't you want to have tested with two gloves since you're trying to verify EVA operable? An astronaut isn't going to have a glove off. So I know you needed one to kind of maneuver things, but did you try with two gloves on?
So the reason we had to have the other hand was because we weren't finished with fabrication at that point. The main purpose of point of CAM is to be one-hand adjustable. So that was the emphasis with the one-hand glove.
Adjustable.
And at the time, it was just not finished. The parts weren't glued yet, but now at this time, it would function properly to be one-hand adjustable.
Okay, one-hand adjustable. Good. And then there was no budget.
We have it in our backup slides.
Okay.
It's just with our
Were you over?
requirements. No. And
Okay.
we wanted, huh? Well under budget, if we can find it, yeah. Whoops. Ah! Yes,
I did for you to mention that you do have a copy of the requirements.
Yeah.
I wish that happened at NASA all the time.
Nice job. I was going to ask, have you guys created a user's guide? So do you have a user's guide for operating this device?
We have a simple concept of operations. We've been working with NASA with our test equipment data package to get some feedback on our something similar to that, but we are still developing it. To
Okay. So will that be developed by the time you travel?
Yes, we have until June, so we will have time since graduation is right around the corner.
Okay. And then I'd like to hear your process for what inspired some of the design decisions and mechanisms. Were any of them really like from your brains you came up, or did you study what the mechanical engineer field has to offer and did a trade space analysis on different options? How did you go about making certain design decisions, especially for the mechanisms that you use?
Right, and I think that goes most heavily with the design of the base subsystem. As you saw with the evolution of the design, the initial design was to create a spring-loaded type of system initially. Through some research, I discovered a similar clamping type of mechanism that it was proposed to NASA for I believe it was a tether attachment that attaches to ISS handrails. I took that design and repurposed it for our design to incorporate all three attachment locations. So the main inspiration came from the tether attachment that was proposed to NASA, but it was repurposed and redesigned to accommodate our needs. Oh, yes, the tether attachment also that I had found had an electric drive motor, and that was adjusted so that it's a spring tension system using the mechanical advantage to provide enough grip force.
Okay.
And then for the ARM subsystem, early on in the design, we actually did go through a pretty complicated trade study on just Revolute or types of joints. So we looked at Revolute joints, ball joints, and stuff like that. We initially determined that the ball joint would give us the most degrees of freedom. But then after trying to fabricate it, we discovered that the ball joint design, since we had really no way to simulate the friction that two plates on a ball would really give us and how much force we could withstand with that, we started fabricating it, and it turned out to be way too weak for our purposes. So then we had to kind of go back, look at that trade study, and look at what some of the other second best options were. And we went with the Revolute joint now just because the limited degrees of freedom, actually, what we originally saw was as a negative point, and ended up being a positive point, so that the EVA user only has to deal with 1 degree of freedom per joint, rather than trying to deal with all 3 at the same time per joint. So that's one of the things that we looked at.
Okay. Just to make sure in your documentation, you give credit where credit is due. So especially for your modifying or using existing designs, say where you got it from. One credit is nice to winning a lawsuit is even nicer. So,
Good job. Interesting. When you guys were doing the demonstration, it looked a little wobbly. Was there any, I didn't read through, requirements on like first modes or vibration? Because the ISS is, humming, literally. So I wonder about the stability of the camera in that case.
The plexiglass surface is actually super wobbly, and that might have made it look a little bit more wobbly than it is. Like on the surface, it actually is not, like, you just held it steady. It's very secure. But to answer your question, we didn't do any sort of research into vibrations on the ISS with this amount.
And the reasoning behind that is because with the challenge, they told us to focus more on testing in the Neutral Buoyancy Lab versus testing for the ISS itself. And if they wanted to use our design, they would update it to meet those kind of specifications.
Okay. And you mentioned glue, which made me think in space, that could be a problem. And then it made me think of the thermal implications. Again, was that not something that was considered?
We didn't have, for the challenge itself, they told us not to focus much on space, so we focused more on what was approved for the NBL.
Okay. Yeah, okay, that's really, yeah. Oh yeah, and then the last one, so you've got these little, grippers, and I would imagine it's gonna be bonked around if it's connected to your belt or, before you're getting on. Was there any testing about or modeling of how much force could be applied to each of these things before failure? Because I don't see any like ANSYS analysis in the backup slides.
There was minimal testing done on that. We did look at some of the forces that the material itself can withstand, and those forces are way beyond anything that could physically be imparted on the system by simply grabbing it and operating the system. Again, that goes into just usability in the Neutral Buoyancy Lab as opposed to actual actual use on the ISS.
All right, guys, really good presentation. I enjoyed it. I enjoyed the project. I like it. It's a cool problem. Just a couple of things that I have. We'll start with the very basic level. A couple of inconsistencies inside your presentation itself with the transitions between people. Some of them you had a transitional slide that said, all right, we're moving on to the next subsystem. And some people got that transition slide, some people didn't. It may be valuable to have a continuous transition slide between people just to kind of keep it comfortable and flowing, but that's really minimal. Getting into a lot of these requirements hurt me a little bit because I'm a test engineer, I like data. So a lot of the testing that you did felt to me a little bit more like an infomercial than an engineering test, right? Like it grips to 3 surfaces, it's great, that's great. How well does it grip to those surfaces? Quantify it for me, you know? And I realize that some of that came from your requirements, so I'm not gonna hold you to that too much. But I did notice one continuous thing, both here and with the video, and this plays out for Sarah's point a little bit. I noticed that you quickly brushed over, we attached to the plate, we attached to the secondary one there, but when we got to the actual, I think it's called the EVA handle, is that correct? EVA handrail. That's the one that you really like to stick to, right? And I think it's because you have the most advantage on that one, and that's where you were comfortable manipulating the arm. Can you manipulate the arm comfortably on the plate as well?
On the plate itself,
on the plate, yep.
it is, you can manipulate it. There is a little bit of freedom within the joint itself.
Yeah, there's quite a bit of movement there, and that right there is what makes me the most uncomfortable, I think, with this system, is that is your highest chance of failure right there of this thing detaching, floating off. The other thing that bothered me is we have, you know, the EVA suit is a very uncomfortable, bulky system, and there's a high chance that this thing is going to get bumped accidentally. Was there any testing or any consideration of that while you were going through this? Can this thing take a knock and hold on?
Due to the fabrication delays, we did not have that time to be able to do it, but we plan to do so in the future.
Okay, sure. The only other question I have, guys, is one of these requirements stood out to me. I may have just managed to miss this somehow, but it reads, and this is requirement 3.2, it reads, each joint shall allow no less than 45-degree range of motion in roll, pitch, and yaw. Can someone speak to that? I only see the 2 roll and pitch.
So the 2 roll and pitch degrees of freedom will be adjusted through here, and then the way that we set up our axis as we were testing with this, we considered yaw the 360-degree rotation of the camera mount itself up here. So it was able to spin in a full 360 degrees, and then each of these is able to move in 90 degrees, or this joint A down here is able to move in 90 degrees in either direction, and then joint B up here, a full 360. And so combined together, they were able to meet the requirement that was pitch and yaw of 45 degrees of freedom from the competition.
Okay, I understand that, but there is another requirement that each joint shall have a locking mechanism, it appears, and a 5-inch diameter handle. So will there be some change to that camera mount that makes it convenient for the astronauts to use and has a locking mechanism as well to comply with that requirement?
If the requirement is worded each joint, then it is an error and it is not a requirement we're going to adhere to or plan to adhere to with the current joint design.
Okay, that's fair. Just to acknowledge that. All right, I think that's all I have, guys. Again, it was really good. I like it. It looks good. It's nice.
So you made the decision to make the arm out of the handhold design, saying that, oh, it's familiar, and so if an astronaut goes and holds on to that, again, there's going to need to be some analysis that they can hold on to it and not like break it off.
So part of that done was the stress durability test where we had the 20-pound force on there. In a previous study done with our old arm joint design, or our old arm design, it was the exact same pin that was connecting the linkage to the joint. And when we did that stress analysis, that unfortunately was not included in the backup slides as it was a previous design from the previous semester. It really should have been through the correlation of the design. But that test done, we applied a 1,000-pound force to it through simulation, and the joint still was able to, or this pin right here was still able to withstand that force without breaking. It was bending, but it did not fracture or anything like that. And so we deemed that able to withstand that force. And future testing we could do is basically take the system from here down and then mount that and apply a load to it and see if it actually performs the way the simulation did.
I don't think there's any other questions, and we got like 5 minutes turnover, so thanks guys.